All right, last part of this section. Now, some of the fancier calculators, you could probably type this in and get it to spit out the result. And that's great for checking your work. But the skill that we're using behind this, you're going to use in a particular situation in Cal 2, maybe at the end of Cal 1. So you do want to be familiar with drawing the triangle, constructing it here, and doing all that. All right, so they give us arctangent, and this is a positive result, so we're going to assume quadrant 1. Well, I mean, tangent's only defined in quadrants 4 and 1, and it's positive, so it must be quadrant 1. Now remember, so dripping on acid. 5. This is our made-up angle. This is the 5. This is the 12. And then they're asking us for the cosine of this angle. So we have the 12, but we need to know the hypotenuse. I have 2 of 3 sides of a right triangle. So hopefully you guys remember, what do we use to find the third side? Pythagorean theorem. So we have A, adjacent, B, opposite, C, hypotenuse. So this is 12 squared plus 25 squared. 12 squared plus 5 squared, which is 25. And 12 is 144. And so we get 169, which actually square roots to be 13. Now, since we're finding the hypotenuse is always assumed to be positive. All right, and then kind of rewind. It wants the cosine. So the cosine of our angle in question here is 12 over 13. So a little bit weird. We have that Pythagorean theorem on the side, which we've done. So all of this we've done in pieces. We're just rolling it all into one problem. All right, 7 down here, same thing. So we're given the tangent, but they're going to ask us for the sine. But again, our tangent is positive, so quadrant 1. Tripping on acid, so it is opposite 7 over 4 for the adjacent. Now Pythagorean theorem, 4 squared plus 7 squared is c squared, so 16 plus 49, 65. All right, so they asked us, what is the sine of the angle we're talking about here? So the sine of this angle is the opposite side, 7 over the square root of 65. Now, Webwork probably should take that. I don't remember if it's actually programmed to force the rationalization, but if we wanted to rationalize it, we'd multiply by the square root of 65 over the square root of 65. And we end up with the sine of theta is 7 square root 65 over 65. Cool. All right, so given this kind of nested function setup, I can use the inside one to set up a triangle and then figure out the sine function of the triangle with the angle I labeled. So example 8 and 9 are going to do similar things, but instead of giving us a ratio of numbers, they're going to give us an expression. But we're going to handle it the exact same way. So our angle is what's inside cosine. So I could rewrite this with sine. So our sine of theta is x over 3. Now, I don't know if this is positive or negative, but I'm going to start up in quadrant 1 just to get a feel for this. So sine is opposite, which we have called x, even though that's a vertical distance, just to be extra weird. And then 3 is our hypotenuse. And then they're asking for the cosine, so now we need to solve for the third side. So our third side is a, so I want to get a by itself. So it's going to look a little weird. Minus the x squared. So I have a squared equals 9 minus x squared. So a equals the square root of 9 minus x squared. Now there is the plus or minus consideration because we applied a square root here. So I'm gonna put that in a different color and I'm gonna highlight it so we can think about that. So arcsine will only spit out values from negative pi over 2 to pi over 2. The cosine of values in quadrant 4 and the cosine of values in quadrant 1 are the same. Just differentiated by reference. They're both positive. So our a value here will only be positive. So we do not have to worry about the negative here. So we just have a is the positive square root of 9 minus x squared. Bam. So they gave us the extra for negative 3 less than or equal to x less than or equal to 3. When we look at our function here, yeah, only the x values between negative 3 and 3 will work. So your brain might be like, what do we do with that? Nothing. It's just there as a restraint. All right, so same song, second verse with number 9 here. So tangent is 4x, and I'm going to sneak it over 1 in there. So we have 4x over here and the number 1 down here. And I would like my hypotenuse. Because they ask for the sine, so I need the hypotenuse to answer sine. So 4x squared plus 1 squared equals c squared. So this is 16. X squared plus 1 equals c squared. So since we are square rooting, we apply the plus or minus for now, and then we're going to go consider, is that needed? And it may very well be needed. Okay. So if I put a negative number in there, then I'm going to get the inverse tangent of some big negative number, which will spit me back out something on the unit circle, some angle measure. And then I can take the sine of that angle measure. And then 16x squared plus 1, I can plug in any numbers I want there. But we would want to differentiate. Both of these equations are actually true for c. It depends on whether we're dealing with a positive x or a negative x. So when x is from 0 to the square root of 14, all right, so from 0 to 14, that is a 1. So when x is positive, c is the positive square root. When x is negative from negative 14 to 0, the length of our c side will be negative 16x squared plus 1. So this means our answer for sine will have some restrictions. So the sine of angle in question is opposite theta is 4x over 16x squared plus 1 with the square root on the bottom. We typically do not rationalize these. What you're going to see in calculus is this setup with all that crud on the bottom is going to lend itself well to a particular kind of integration. So we do not rationalize this square root on the bottom. So this should be the acceptable answer in web work. If it even asks one of these in web work, it may not. All right, call this one there.